Can you guys hear me?
Yeah.
It's not yet live. It's not yet on live. We are live. Good. Okay, let's get started. So the main agenda today will be the Lovasz theta function, but we'll wrap up some things which we talked about expanders towards the end of last lecture. So let's do a quick recap of what we did from last lecture. That is de-randomization, using expanders. So we proved the following we've proved the following theorem due to Karp, Pippinger, and Suxer. Suppose there exists a greater than 1 such that if G n vertex deregular graph is an n by 2 a expander, vertex expander. That is, all sets of size at most n by 2 expand by at least a factor a. Then for any b subset of vertices, so that size of b is less than half one, we proved the following, that is, if you pick a random r from the vertex set, and if you look at the ball of radius t centered around the ball, what is the probability that this ball is in the set B? We showed that this is at most 1 by 2 to the power a power t. This was the theorem which we proved. It was the end of last lecture. So what does this theorem state? Formally, from this one, what it states is the following. So let's think of this. Straight lines. This is the vertex set, which is vertex set, and you have some b here, which is not too large. Now you pick a random r, and you take a ball of radius brt around it. You're asking what's the probability that if you take a vertex and take a ball around it, a ball, and what do I mean by a ball? The ball is based on the walk on the graph. That is, you take all the vertices which are at most distance t from this one and ask, can the entire ball be in this set? And we saw that this is the probability of this happening is very, very low. And what was the major application of this? The major application of this was towards RP error reduction. So to reduce the error of an RP algorithm, in particular, if you want to reduce the error from half to delta, so we would want to set 1 by 2 power a power t to be less than or equal to delta. Equivalently, just set t to be the ceiling of log 1 over delta minus 1 by log a. We set it this way, then this would be satisfied, and we would get this one. So if we take a walk, if you want the error to be less than delta, we basically take a walk of this larger radius. But then there's another caveat to observe, that is, we need to run the algorithm and all the vertices of the ball. And if the algorithm needs to be efficient, we need to check that this number of repetitions is actually polynomial. And what is the size of the ball, DRT, is at most d plus 1 per t. And this is polynomial as long as t is order log n. If t goes beyond or log n, the order log n, this is going to become super polynomial. So we can work with t. So now you need to 1 and 2 tell you. 1 tell you can get any error by taking t to be log 1 over delta minus 1 by log a. A is constant, d is constant. Remember the way we construct the graph, a is constant, d is constant. Therefore, we can get, in order to get this, we can set delta to be any inverse polynomial. That is, hence, delta being 1 over polynomial, that is any inverse polynomial is achieved. You can't do better than that. You can't make it smaller than that. Any inverse polynomial is achievable by above. Okay. So the question we'll ask, sort of the question which we spend the first 20 minutes or so, is what about smaller delta? Can I reduce the error even smaller? What smaller delta? I won't be able to do it without adding a random bit. Possibly at the cost of a few additional random bits. This is what we're going to ask. To get up to polynomial error, inverse polynomial error, we didn't even spend one extra random bit. Here I will possibly spend a few random bits. And in fact, the algorithm is going to be fairly simple. What we will do is, previously, what did we do? Once again, we had this picture. There was this bad set B. And we took a ball of radius t. Instead of taking a ball of radius t, we will take a walk of radius t and just do the thing. Instead of on the entire ball, we will just take a walk and run the algorithm on all vertices along the walk. So replace ball of radius t with walk of radius t. This will actually be a stronger lemma than what we proved. We'll prove the following lemma, which is called the hitting set lemma for random walk on expanders. This is due to iTie, Lovasz, and Zemeridi. And what does this say? I will state it more generally, not just for deregular graphs, but for any Markov chain which has bounded spectral gap. So let W be any reversible random walk. And omega be the maximum of the second and the second largest eigenvalue, second largest and the smallest absolute value of the largest eigenvalue. Let B be any subset of the vertices, and let pi of B be equal. Let's define it to be equal to what I'll call mu. That's the probability of the bad set. This one. And let x1, x2, xt be a random walk of length t starting at xt, which is distributed according to the stationary distribution. So the first one you pick according to the stationary, and then you take a t-step walk. So, and what we look at is the probability that for all. So this is the random variable is over x1 to xt. For all I in t, xi is in t, we'll upper bound this. Now suppose the walk was actually independent. It was not a, it was, so every vertex was picked uniformly with probability pi. Not uniformly with probability according to the stationary distribution. It was picked according to pi. Then what would this be? This is just be mu to the power t, because you're just asking, you're picking t independent vertices and you're asking what's the probability that each of them lies in B. Each of them being in B is mu to the power mu. Therefore, all of them lie in T is mu to the power T. What we'll show is it's almost the same thing. We'll show it is mu into mu plus omega into 1 minus mu whole power T minus mu. That's the theorem which we'll show. So it's almost as good as we want, except for this error term. If this error term had not been there, it would exactly been as if you're picking independent. So it's saying it's not mu, but there's an error of omega into 1 minus mu. Notice that this quantity is still a number less than 1, because mu plus 1 minus mu is equal to 1. Therefore, this quantity is less than 1. Therefore, instead of mu to the power t, we have mu into something else to the power t minus 1, where this quantity is, so it's still going down exponentially in t as you take t steps. Okay, any questions on this? So in particular, let's, even before we go to the proof, let's make a couple of remarks and then jump into the proof of this. Therefore, think of mu as typically something like half or something. It's the bad set, and omega is some number less than 1. Therefore, mu plus omega into 1 minus mu is what it is. It is basically 1 plus omega by 2, and this is some number less than this one. Therefore, this probability is basically half into, so it's half power t into 1 plus omega. Am I right? 1 plus omega per t minus 1. This is something exponentially small, and this is exponential in minus t.
Prahladh, is there also an x0? Like
no. So x1, x2, xt.
But there are t plus 1 terms on the right hand side, right?
Where in the right hand side?
It's like t plus 1 of them. So for the first mu comes from x0, right? This is just some.
No. The first mu comes from x. So I started the walk with x1. So x1, x2, xt, and therefore this is mu into t power minus 1. No.
Yeah. Or t minus 1. Okay. That says t minus 1. Okay.
Yeah, that's t.
I was reading it as t somehow. Yeah. Okay.
Yeah, this is t minus 1. Okay. So you can.
Sorry,
somebody else had a question?
Yeah, wait. Can you say why? How did we get that term inside the bracket?
Which term inside the bracket?
The mu plus this
we
omega error.
We haven't proved this.
Yeah, I thought I lost somewhere.
I will spend 10 minutes proving this shortly.
All right.
Yeah. So this is going to be a stronger statement. It is stating that it's almost like if it were independent, it was mu to the power t. If the walk were independent, it was not a random walk. It is each vertex you picked independently, it's mu power t. Claiming that even though you don't pick it independently, you're picking it in a very dependent fashion. You're picking it from a walk. It is still something which goes down exponentially in t. Okay. So in particular, let's look at so error is still going down exponentially in t, but let's look at the number of random coins being expended. Random coins being expended is the random coins. Let's write it just for the case of nd 1 minus omega expander. I'm not going to write it for an arbitrary random walk. In this case, the first vertex, it's log n. You have to expend log n bits to expend the first guy. Then you spend t minus 1 into log d, because you have to take a random step. This is something like log n plus order t. So notice that this is in contrast to independent random. If you picked independently, it was order t times log n. So the extra randomness you're paying is only additive in t. It's not multiplicative in t. That's the important. That's the key. That's the key advantage of using random walks and expanders to reduce error rather than doing it on this one. Okay. Up to inverse polynomial error, we didn't have to pay any additional thing. After inverse polynomial error, if you now want the error to go down, say you want to get the error, it is not inverse polynomial, but say inverse exponential or quasi polynomial, whatever you expend, whatever t you want, you can get that t, but just paying that much amount of extra random bits. Usually, if you wanted to do that in the independent thing, you will pay a multiplicative factor in t. Here, you are paying only an additive factor in t. Is that okay? Any questions? If not, we will jump into the proof of the heating set lemma. Okay. Okay, so let's go into the proof. So what I want to bound is this quantity. The star is what. So let's go to the proof of the heating set lemma. So let's write down what star is. What is star? Star is the probability that if you take t steps in a random walk, that is, you land all the t steps happen to be in the bad set B. So I'm just going to write this exhaustively. Write this as I1, I2, IT. These are the t steps I like. It's a probability that x1 is I1 and x2 is I2 and xt is IT. So go over all possible t vertices in B and ask what is the probability that you see this particular sequence of vertices in the random walk. This is exactly what star is. But this, now you can write this down. This is exactly summation I1, I2, IT in B. This is a probability that the first vertex you see is pi I1. That's how you pick it. Then you have to make the transition from I1 to I2. Then you have to make the transition from I2 to I3. And so on up to IT minus 1 to IT. Okay. Just written down explicitly what this probability is. Now, I don't like this summation. This summation is over B. I would prefer it to be over all the vertices, not just in B. And so for this, we'll change the way I write the summation a slight way so that I can write it over all B. For this, we'll introduce this matrix P, which is just diag of the indicator of B. So P looks something like this. If this is B complement, P complement. So I'm splitting the matrix into 4 parts. This is B complement, B complement. This part, it's just identity. Here it's 0, 0, 0. So once I do this will sort of say, I can sort of write this summation as now I1, I2, IT. These are unconstrained vertices. Pi I1, P I1, I1, W I1, I2, P I2, I2. P is checking whether you are in the set or not. If it is not, that term gets vanishes away. So WIT minus 1, IT, PIT, IT. The people with me so far? This, if you look at it, this is nothing but summation over all I. How do I write this? How do I want to write this? I just want to, this is just the L1 norm of the vector pi p w p to the t minus 1, the L1 norm of this vector. People, or also I can equivalently in the, it will be nicer to write it in our pi inner product. This is nothing but the quantity t minus 1, 1, 1 in the pi inner product. Okay, where 1 is the just the all ones vector. Any questions so far? Okay, so we want to bound this. So to bound this, we want to put an upper bound on this. We have an inner product. A natural thing to do is to do Cauchy-Schwarz. So let's apply Cauchy-Schwarz, but let's be a little clever before applying the Cauchy-Schwarz. So what I want to say is this is the same actually, because this both these vectors are only supported on, this vector is only supported on this vector because of the last pi, it's only supported on vertices in B. It just zeroes out everything outside B. This is the same as actually PWP T minus 1, 1, 1B. Nothing has changed by doing this. And now if you apply Cauchy-Schwarz, this is just PWP T minus 1, 1, the 2 norm of this vector, 1D, the 2 norm of this vector. This I'm going to write it in a slightly cleverer fashion. I'm going to write this as PWP to the T minus 1 into P1 2 pi. And this one is exactly root mu. 1B's 2 pi norm is root mu. And the reason I'm able to do this step is because P square is equal to P. I've introduced several P's in between, and the reason I'm able to do it is because P square equals P. Okay. So this is the quantity I want to bound. So this is, once again, it is PWP to the T minus 1. This is IP of I1 is just this 2 pi square root mu. Are people with me so far? Any questions? Now, what we want to do is analyze this expression. I want to analyze this expression. So let's do, for a general matrix, I'm going to write this. For a general matrix, I'm going to define the following. For a general square matrix, M, we'll define the norm of a matrix. So far, we only define the norm of a vector. I'm going to define the norm of a matrix to be, I think this was done by, I'm going to define it as the maximum. Look at how much it can stretch any vector. Take the maximum over all x, mx, the 2 pi norm of x by 2 pi. If you notice it, this will exactly be the largest eigenvalue of, in fact, this is the largest eigenvalue, or more actually the largest singular value of, this is exactly the largest singular value of, let's call it eigen, let's leave it at this. This is the largest eigenvalue because I'm doing it in this inner product. Value, and I'm going to define it this way. And an easy observation of this definition is the fact that M1 plus M2, this is a norm. Actually, this is less than M1 2 pi plus M2 2 pi. And this just follows from the definition. I'll just read it off the definition that it has this property. And we'll use this. So now coming back to returning to star, we have that star, which we saw was less than or equal to PWP to the t minus 1 1b 2 pi times square root mu. This, by the definition of this one, I can write it as pwp to the t minus 1 2 pi 1b 2 pi into root mu. This, the norm of a matrix power is the matrix norm raised to that power. That's easy to see once again by the definition. So this is just pwp 2 pi to the t minus 1 into, this was mu which you already calculated, this is mu. Okay. So to complete the proof, suffices to show norm of PWP, the 2 pi norm of PWP is less than or equal to mu plus omega 1 minus. I'm going to write this in a slightly different fashion and we'll prove it shortly. I will prove it to be 1 minus omega mu plus omega. This is the same thing as what was written. We'll prove. This is what we need to prove. So if we prove this, we will be done. That's the final, that was the goal of our thing. Let's do a warm up. Let's say if W were not the mark or random walk matrix, but it was actually in which each vertex was picked independently according to pi. That case, we can actually prove this is at most mu. And then we will show how to modify that proof to get it to be the full random walk matrix. So let's start off with a warm-up case. Warm-up case when W, the random walk, is independent. That is, each vertex is it's not a Markov chain. That is, you just pick according to the independent. This one independent according to the stationary. Let's call this W ind. What is the matrix for this? How does the matrix for this look like? If each vertex I'm going to pick it independently according to pi, how does the matrix for this look like? So any vertex, I forget where I am and I pick a neighbor distributed according to pi. So how does W end look like, the matrix corresponding to W end? Varun, I can't hear you.
Oh, sorry. Every row will be this stationary distribution.
Yeah, so this will just be this thing. Every row will be the same stationary distribution. So this will be, W end will be this object. Or equivalently, sometimes this is written as J times pi, where pi is diag of pi. Now let's look at what happens when you work with W ind P. What does this guy look like? This is pre-multiplying and post-multiplying by this IB vector, the diag of IB. So if you notice it, this quantity will just be once again B complement, B complement. The post-multiplication will zero out some columns, the pre-multiplication will zero out some rows. So what you'll just have is pi restricted to B. That's what you'll have in this square part. And 0, 0. It's not the normalized pi restricted. It is just pi on the B part. It's going to be this. This is going to be this vector. The PW and P is going to be this particular thing. Notice it's a rank 1 matrix. There's only one vector. There's only one. This is a rank 1 matrix. It has just take the first column. Every other column is a scaling of that column. If they take the first row, every other row is a is a scaling of that row. Either it's the same row or it is the row multiplied by 0. And it's not hard to see for this guy. It's a rank 1, and if you multiply it, so if you multiply it by 111 IB, if you multiply by this, what you will actually get is IB multiplied by pi b. Its eigenvector is IB, and the corresponding eigenvalue is pi b. And this is the singular effect. So this will tell you that PW ind P is exactly equal to its L2 norm is equal to pi b, which is mu, which is exactly what we wanted to prove. That is, in the warm-up case, this is what we wanted to have, and good. So we have this. What we want to now show, let's go back to the more general setting. So this is the warm-up setting in which let's go to the more general setting. W is a random walk matrix. No, it's a random walk matrix. A matrix is fully specified by the way it acts on the basis vectors. Once you specify that, a matrix is fully specified, and we have a nice basis vectors. The right eigenvectors form a nice basis vector. So in particular, so let's look at, so we had v1, v2, vn, and v1 in fact was the all ones vectors. These form an eigenvector with eigenvalues. What were the eigenvalues? The eigenvalues were 1, omega 2, all the way up to omega n. These were the eigenvalues for this, and this was greater than or equal to minus 1. These were the eigenvalues. So W is fully specified by just saying that V1 is going to V1, V2 is going to omega V2, Vn is going to omega Vn. If I specify this specifies W. If I say W is the operator which takes these vectors to these vectors, that fully specifies W because these form a basis. Let's see what W independent was. W independent is exactly, let's see what its action is on these vectors. It is the action which takes V1 to V1, but V2 and all to 0. This is exactly W end. If you stare at it, if you write down, this is exactly what W end is. Now I'm going to build up a new matrix called W error. So I'm going to write W as a combination of W independent. So I'm going to view it as a W end plus something. So I'm going to write it as another, this one which takes V1 to omega V1, V2 to omega 2 V2, V3 to omega 3 V3, and Vn to omega n Vn. I want to say, when I write it this way, W is exactly 1 minus omega W ind plus WE. Do people agree? This one. Why did I write it as 1 minus EW ind? We'll come to it in a second. So let's look at WE. I understand the, so W ind is something I understand quite well. This is what we did previously. We are going to eventually apply the triangle inequality to understand the L2 norm of the PW pi P. We'll write it as PW ind P plus PWEP. We're going to split it into two parts. PW ind P, I know how to do it. We already found it out. PWEP, I need to find out. But let's look at what WEP is. So WEP, WE is the vector which we already defined. So let's look at it. WE. So WE of any x. WE of any x. Let's see. So let's take any x. Let x be summation alpha I vi. And let's understand what does WE do to X. This is exactly going to be alpha 1 omega V1 plus I going from 2 to n alpha I omega I Vi. This is how that's exactly how WE has been defined to be. So let's look at what is, therefore, mod of x2 pi in this world was exactly summation alpha I square. What is WE x in the 2 pi world? This will be summation alpha I Wi square I going from 2 to n plus alpha 1 square omega square. Notice that because the way we chose omega, this is less than or equal to omega times summation alpha I square. I going from 1 to n. The reason for choosing WE, this is less than or equal to omega times omega square times x2 pi square. This tells you hence WE's 2 pi norm is always less than or equal to omega. This is all I wanted to conclude. So now let's return to the proof. We needed to bound PWP. But PWP, we wrote it as P of 1 minus omega W ind plus WE P 2 pi. This is less than or equal, by triangle inequality, this is less than 1 minus omega P W ind P 2 pi plus PWE P 2 pi. This, we saw this was exactly mu. We had already proved this, W and P. What is this? This is P2 pi into WE 2 pi into P2. It's at most this quantity. That each of them can only scale it down by so much. P is at most 1. The norm of P is 1. Norm of WE is omega. Therefore, this quantity is less than or equal to 1 minus omega mu plus omega, which is exactly what we wanted. Hence, PWP 2 pi is less than or equal to 1 minus omega mu plus mu. An equivalent way of writing this is mu plus omega 1 minus. Are people with me? So this is a nice way, this proof, there's one nice technique going on here. This proof, what we have done is this matrix decomposition. And this is a useful technique to keep in mind. This is what's called the matrix decomposition. It's sometimes quite useful to that is.
W is not all the omegas. It's omega
What?
2, omega 3.
Huh?
Just about this small. So in the description of W, the eigenvalues are omega 2 to omega n. On the right hand side, it's just typo.
What?
I just like the description of W, just
Yes.
above W.
Yeah. So this is you mean here?
Yeah.
Here, you mean here? Sorry, here.
Yeah.
Here it's omega 2, omega n, right? Yeah. So.
And one more thing that we're using is this thing that you can do the eigenvalue decomposition orthogonally with the pi. So
what?
So we're also using the orthogonal decomposition with respect to the pi inner product.
Yeah. So we are using that. This is the random walk. We are very much using the fact that these guys form. This is a set of right eigenvectors which are orthonormal under the pi inner product. Yeah. This proof is, like several proofs we have done in the past. It's using this fact repeated.
Yeah.
Okay. So this. going to conclude the thing on expander walk. So this tells you that you must get this. By the way, this was a hitting set lemma. It was RP error reduction. You can think of doing this for BPP error reduction. So there's something called the Chernoff bound on random walk on expanders. And the homework, you can prove this along the same lines which I said now. Here, this one. But what the homework will show how to reduce the Chernoff bound proof, at least the weaker version of the Chernoff bound statement to this. There will be a homework proof in which you will actually use the hitting set lemma to prove the Chernoff bound for expander walks. A weaker version, you can prove a stronger version by actually going into the sort of proof which we just did and actually doing it. But the weaker version you can get by the weak, you'll see a weaker version in the homework. Okay, so that concludes our discussion on expanders. We'll start a new topic called the Lovasz theta function. Okay. So, since this was not part of my original list of topics, but we decided to include it in honor of Lovash's Nobel Prize this year. And also, in some sense, we did a fair amount of semi-definite programming. In some sense, this is based off a paper. This is based off a paper by Lazzi in '79 called "On the Shannon Capacity of a Graph." So we will soon see what the Shannon capacity. He wanted to analyze the Shannon capacity of a graph. Is not a very well understood concept. We do not know how to compute it. So what he gave an upper bound to compute the Shannon capacity of a graph, and it relates to something called, we'll soon see it relates to something called the independent set. So he defined this new function, which is now called Lovasz theta function in Lovash's honor. And this function was an upper bound. It was an upper bound on the Shannon capacity graph. For graphs, it was able to exactly capture the Shannon capacity. And furthermore, this was a quantity that was computable, unlike certain other quantities, for example, like the Shannon capacity of a graph or some quantities like, so we will see. So what we will eventually see over today's lecture and possibly a little more, given a graph, there are multiple quantities you can talk about. One is alpha G, which is the size of the largest independent set. The other is, so let's write down several things. Other thing is called omega G, which is the size of the largest peak. And notice that omega of G complement is exactly equal to alpha of G. Therefore, I will not talk about clique number at all. I'll just talk about independent set because I can go over the complement graph. Then there's chi G, which is the chromatic number of a graph. What is this? It's the minimum number of colors required to color the vertices of the graph so that no two vertices of an edge, every edge receives, no edge is monochromatic. An equivalent way of stating this is a way of partitioning the graph into the minimum number of independent sets. That's an equivalent way of stating this, IG. And it should be easy. It's an easy observation to show that omega G is always less than or equal to chi G. Any clique can pick at most one vertex from each of the color classes. It cannot pick more than two vertices from the color class because then there's no edge between them. So any clique particularly the largest clique, can pick at most one vertex from each of the color classes. Therefore, omega G is always less than chi G. Now, just like alpha G and omega G are sort of for the graph and the complementary graph, we can define something called chi prime G, which is called the clique cover number. Which is the minimum number of cliques that partitions the graph. So you want to decompose the graph, unlike the chromatic number, you want to decompose the graph into cliques such that every vertex is present in one clique or the other. Across the clique, there might be edges, there might not be edges, I don't care. But within a clique, they must, all the edges must be present. That partition the graph, the partition the vertex. And for the reasons with the same reasons. So clearly, chi prime of G is equal to chi G complement. The way I have defined it, and so hence we have the observation that alpha G is less than or equal to chi prime of G. That just follows from the omega G is less than chi G, therefore alpha G is less than or equal to chi prime G. All these four quantities are NP hard to compute. These are all NP hard to compute. What Lovasz did was actually introduced a new function which we'll call theta G. We'll introduce this is a Lovasz theta function. For every graph, he defined quantity. And the nice thing about this quantity are two remarkable properties. One is theta G is efficiently computable. Rather, efficiently up to, that is, you can come to compute, that is, you can compute it to any accuracy you want. Basically, he will write a theta G as a semi-definite program, and semi-definite programs you can compute it to arbitrary accuracy. It is basically write in a given a. We will see an SDP formulation for.
Right. No,
sorry, I didn't. Was that a question? And then we showed this following sandwich theorem. That is, even though this is a computable quantity.
Going well, but I'm slightly behind that working. If I should finish everything by December, and then I shall do one and then waiting for the and by next November, keep long. Now, what is doing music for is okay.
Okay. The sandwich theorem, he'll show us that theta G is sandwiched between chi G complement and alpha G. Though it's a computable quantity, it's going to be sandwiched between two things which we don't know how to compute efficiently. Okay. So we will see more or less we will see this all of this today. It will be an upper bound on the independent set of a graph, and the motivation for Lovasz to do this was to understand what's called the Shannon capacity of a graph. So let's just jump into that, try to understand what the Shannon capacity of a graph is, find out that, and then eventually we'll come to the SDP formulation of theta and also prove the sandwich theorem. So that will be the goal for the remaining 30 minutes or so. This might flow into the next lecture. So let's start what I'm going to call the Shannon capacity of a graph. So let's think of, suppose you have an input channel X and an output channel Y. This is an input. Output. Sorry, there's an input alphabet X and an output alphabet Y, and the channel takes an input alphabet and produces a possible output alphabet. So for instance, let's take 0, 1, 2, 3, 4. These are suppose my input alphabet, I had 5 different alphabets, 0, 1, 2, 3, 4. That was my input alphabet. And the output alphabet was also 0, 1, 2, 3, 4. Now, a perfect channel is when you send in 0, it sends out 0 at the other end. Send out 1 at the other end. That is, a perfect channel is basically a matching. What I want to see a matching. Therefore, say if I write something, what I read I write something and then I go and listen, I will read it. I will read exactly what I have written. The channel hasn't corrupted anything. But the channel possibly misses up certain things. For example, as a typewriter, when you type a particular key stroke, it might not only type either that key or even the adjacent key. There's a possibility of a confusion happening. So let's assume this sort of, I'm going to draw the edges in this graph are going to sort of represent. If I give this as the input character, what are the possible output characters that the channel could have output? Okay. I'm going to draw this sort of a thing. Now I give, so this is the channel. The channel is, so I tell you I have a channel which does this, which give me this. By the way, the input and output characters need not be the same set of characters. It could be a different set of characters. I write A, B, C, D, it writes out alpha, beta, gamma. That's okay. As long as if it was a matching, I can read what it goes. It's just a different way of writing the letters. Now, but now there is some confusion that happens because given an output alphabet, there could be two potential input alphabets that rise it. So let's take a very specific, I should have this. So let's assume 0 goes to, it does the right things. So it does these things. But in addition to that, when you send 0, there's also a possibility that it outputs 1. When you send 1, it's a possibility that it outputs 2. When you send 2, it outputs 3. 3, it outputs 4. And 4, it outputs 0. Suppose this confusion is also there. So the channel potentially does this. When you send in a 0, it either sends outputs a 0 or a 1. If it sends it any I, it sends in outputs either I or I plus 1, mod 5. But this I can put this as anything. Now the point is I want to say, well, so I give this, I want to ask what is, if I have such a channel, what's the actual alphabet? What are the number of words I can actually, what's the number of letters? Suppose I use this channel, what's the number of letters I can transmit without any error? Without any error. For example, now if I get 0 at the other end, I do not know if it was 0 or that 0 could have been either a 0 or a 4. You don't know what it is. So what we'll do is we'll draw this notion of a confusability graph. Confusability graph. The vertices of this graph is the input alphabet, and x comma y is in the edge. If you put an edge between x and y, if there is a possibility to confuse between x and y. That is, there exists, sorry, I should not have put x comma y, let's put x1 comma x2. If there exists a y in the output alphabet such that x1 goes to y as well as x2 goes to y, and x1 is not equal to x2. So I put an edge between two distinct input alphabets if there's a possibility to confuse them. Okay. So what is the confusability graph for this particular thing? If you notice, the confusability graph is exactly the cycle. C5. So for this particular thing, so given any particular channel, a channel is just something like this. It possibly mixes up some letters. I give you a channel. A channel is this bipartite graph. This is what I'm going to call a channel. It's this bipartite graph. X, B, and E. This is a bipartite graph. And from that, I build a confusability graph. Now, looking at the confusability graph, how many input alphabets can you actually transmit faithfully? That is, without, I want to send it so that there's no confusion. Certainly, I can't send all 5 of them because it's going to get all confused. So suppose can I send 2? Can I pick 2 input alphabets such that if I send them across, there will be no confusion. No matter what the output is, I will be able to find out which 2 input alphabets, which of the 2 input alphabets I sent
0 and 2.
0 and
2.
2. So in particular, what I want to say is, suppose I picked an independent set in this confusability graph. You pick any independent set in the confusability graph. I claim that if you work with just this as your alphabet, though the alphabet was all of X, you work with just the vertices corresponding to the independent set. If you just sent this, there will be no confusion. At the end of it, no matter what you get, you will be able to recover it because this is an independent set. Are people with me in this?
So we can, so here the confusability graph is telling us that if you are getting 0 as an output, then it could have been either 0 or 4.
No, I put an edge between two input alphabets if I can get confused between them. If there is an output alphabet that arises from both these input alphabets.
Right.
So if there's a possibility of confusion between these two input alphabets, then I put an edge between them.
So if you were sending 0 and 2.
If I send 0 and 2.
I mean, you won't confuse these two, but I mean, those can be fudged to some other alphabet. So how do you recover it then?
No. 0. So now I only send 0 or 2. I only send 0 or 2. So the other end, I would either get 0, 1 or I would get 2, 3. No matter what I get this, I will be able to figure out whether, so both the reader and the writer know that I'm only working with 0 and 2 now. No matter how I write it, we will be able to figure it out because I have restricted my alphabet to the independent set.
Yeah, makes sense. Okay.
That's all I'm claiming. So if your for what I want to say is for one letter words, and in fact, alpha G is the largest number of words I can transmit. On the channel without any error. This is the maximum number of words. You choose any independent set that will work. You could have chosen 0, 2, 1, 3, 2, 4. Any of this would have worked. This is a one. Okay. Now suppose I want to send 2-letter words. We could do the same thing. We could send the first letter this way, the second letter this way. But I want to say 2-letter words. You can do a little more than this. So suppose you go to 2-letter words. Suppose your 2-letter words. Of course, you could send 4 now because alpha C5. So alpha of C5 was 2. You could send 4 words. Any word formed out of 0 and 2, any 2-letter words formed out of 0 and 2, which are 4 in number, can all be decoded correctly on the other side. Okay, but I want to claim actually you can do slightly more than that. So let's look at, so I want to give you an example. So suppose you work with 2-letter words. So I want to claim, suppose the 2-letter, so we said 4 you can do. 00, 02, 20, 22. If I transmit them across this channel, then no matter how I write them, no matter how they get written, from the output, I can just read it off what I had sent. I will be able to find out which of the 4 words I had written, which of the 4 words were input on the channel. You with me? But I want to say, actually, if I care for 2-letter words, I can do a little more than that. So I want to claim, let's look at the words 00, 12, 24, 32, and 43. Can I confuse 00 for 12? I cannot confuse 00 for 12 because 0 could have been confused with 1, but 2 could not have. So if I had got, so suppose I want to claim that, suppose these were the 5 input words I was going to write. Now, no matter what I send across, I want to claim there's no way 00 can be confused for 12. Why? There's nothing There's no potential, there is no sequence of two output words that both 0, 0 and 1, 2 could have led to. 0, 0 could have led to 0, 1, 1, 1, 1, 0. These are the four possibilities 0, 0 could have led to. 1, 2 could have led to four possibilities. Notice that there's no intersection between those two. So these two are actually will look very, the set of words if you send 0, 0 across on this channel, it can give rise to any one of four words. And those four words are completely different from the four words that 1, 2 could have given rise to. And you check the same thing. So 0, 0 and 1, 2 are different. Similarly, you can check that 2, 4 and 1, 2 are also different. 3, 2 and 0, 0, 3, 2, 1, 2, 3, 2, 2, 4 are different. 4, 3. Every pair in this are different or can be distinguished. And what do I mean by that? For every pair in this, if you take the four possible output words for one element and four possible for the other one, there is no common element between them. There's no way you can get confused. And you can actually check this. So let's try to make this a little formal. What I'm actually working right now is we had the G, which was a confusability graph. And I'm going to define something called G tensor twice. I'm going to tensor G 2 times. It's not the usual tensor. This is what I'm going to call the strong product. Let's write this way. So let's actually put a square this way to distinguish from the usual tensor graph. So G tensor. So actually we'll be doing G tensor. This is the strong product. I'm going to define this object. So G itself is some vertex E. H is some other vertex W and F. And the strong the vertex set of the strong product is just the Cartesian. It has all pairs of vertices, but what are the edges? So I want to say U1, U2, comma V1, V2 belongs to the edge of G tensor H if the following conditions are met. 1, U1, U2 is not equal to V1, V2. Certainly, it's not the same pair of vertices. And 2, for all I in 2, either Ui is equal to Vi or Ui Vi belongs to Ei. So I should have possibly called this E1, E1 and W2. So an edge in the strong product exists if between a pair of vertices, if for every induced pair, you should either be making a move or you should not, or you should be the same vertex. And on at least one of them, you should be making a move because you can't be the same vertex. U2 can't be equal to V1, V2. This is what I mean by the strong product. And if you recall, if G is the confusability graph for one letter words, strong product G is the confusability graph for two. You're asking, is there a possibility for confusion when you write two things? Is there a possibility? So all I'm claiming is, and I'm going to write G strong product 2. In general, we're going to define G strong product K to be equal to G if K equals 1, and it is G strong product K minus 1 strong product G for K greater than 1. So it's just a repeated strong product taking. And it's an easy observation that G strong product K is the confusability graph for K letter words. Because you're asking, can you confuse them? The question is, when can you confuse two K letter words? You're asking, is this K symbol word can be confused with this K symbol? You're asking every pair, either they should be the same or they should have a potential for getting confused. That's what you mean. And that's exactly what the strong product is capturing. So you have U1, U2, UK and V1, V2, VK. Question is, can you get confused between these two? You can get confused between these two if for every UI and VI are either the same or UI and VI can be confused with each other. And that's exactly how I define the strong product. And so notice, so if I want to send K letter words, the best thing I could do is the independent set for that corresponding graph. So the maximum number of words, maximum number of K letter words that can be transmitted on this channel error free. Error free is alpha of G tensor K. That should be clear. Is this okay? And the following is an easy claim to see, that is alpha of G tensor H, G strong product H is greater than or equal to alpha G times alpha H. That should be easy. Take the two independent sets in G and H and their product will be an independent set in G tensor H. So G strong product H. It can only be larger than that. That is going to be, this is an easy claim too. This claim is an easy claim. And what? So in principle, this can become larger and larger. And that's why alpha G tensor 2, G strong product 2 was 5. Whereas alpha G into alpha G was only 2 into 2, 4. Therefore, if you send 2 letter words, you could actually send 5 words, not 4 words. You could do a little better. And the Shannon capacity of a graph is defined to be Shannon capacity of a graph G is defined to be, it's called sigma G. It's the supremum over all K of log of alpha G tensor K by K. You're sort of amortizing this fact. There is a number of the alphabet words you can send. So the number of words, the actual number of words is actually log of it, but because you're going by K, you're amortizing it. This can be because of the previous claim, this can actually be shown. This is actually limit K of the same quantity. This is not hard to see. And this is what is called the Shannon capacity of a graph. And what we already saw was alpha of C5 is greater than or equal to log 2. But we know it's also greater than or equal to log 5 by 2. Because, sorry, the alpha, it's not alpha. What did you see? So what am I writing? For C5, for the case of C5, we saw that alpha of C5 is 2. Alpha of C5 product 2, we saw an independent set of at least 5. And there could be a larger independent set. So this implies that sigma of C5 is at least log phi by 2. It could be more. As you keep going larger, it could be more. But one thing, notice that sigma, because of the couple of observations we can do, sigma g is always larger than alpha g. This is just the base case. The sigma g is larger than alpha g. It can be much, much larger, but it can no way be larger than log of v. That is, any alpha of any g power k is at most v power k. The totally independent set can be number of vertices to the power k, which is log of v. Therefore, you have this bound. Therefore, sigma g is lying between these two quantities. And Shannon asked, even for very simple graphs, can we compute sigma of a given graph? For example, Shannon left it as an open question. What is sigma phi, c phi? We know it's larger than log phi by 2, but can you compute it exactly? This was a question which Shannon asked. And Lovash had introduced the theta function basically to answer this question. He wanted to show what the Shannon capacity of this graph is. So we will work with something that's not the Shannon, almost the Shannon capacity, but we'll work with not, so sigma g instead of, so sigma g is going to be limit of k tends to infinity of alpha g power k, the whole to the power 1 over k. So this is, if you recall, this is just 2 power sigma g. So we'll work with capital sigma g instead of small sigma g instead. It's just the same. It's just the 2 power whatever exponent we had instead of sigma g. So we'll work with this quantity. And Lovash used the theta function, the famous theorem of Lovash. He used the theta function to prove that sigma c phi is actually equal to square root phi. Okay. Okay. And what we will see in the remaining 10 minutes and the next part, the beginning of next lecture, is actually we will give a formal proof of this fact. We'll give a full proof of this one. And to prove this, Lovash introduced the theta function, and he gave and he showed that the theta function is not only a quantity he proved, but he didn't stop with that. He gave an SDP formulation of the theta function, and this is the first semi-definite program that was ever written. So this was said that this upper bound is not just a upper bound for this problem. He gave this, then he showed that there was a sandwich theorem. He did more with this. He came up with this function and showed that it has several nice properties. And this eventually led to this revolution of semi-definite programs that happened a decade or so later. Okay.
I mean, just so Grothendieck constant thing came earlier, or maybe it is not explicitly written as.
Grothendieck is before Lovash?
I'm not sure.
Okay.
But
Okay.
maybe.
Okay.
Not
So,
sure.
okay.
But one of the first two.
Okay, but by the way, both of them are independent. This was not. They both had formulations which were at that point of time. They wrote it down as they were trying to understand something else. They wrote formulations which were eventually what we call semi-definite formulations of this problem. They were done independently. It could be that
And I think this even before there were algorithms. This is before Kashian.
Okay.
Or maybe around the same time. But yeah, so that is even more interesting, even though there was not a.
Okay. So now so we already know that sigma c phi. So what do we know? Sigma c phi we know is larger than square root phi because we gave this one for it, but it's also smaller than phi because that's the size of the graph. It can know about this. What we want to give is a better upper bound. We want to get the upper bound to square root phi. We can get that. then we exactly compute C5. And Lovasz wanted to do this. So Lovasz wanted, so sigma C5 is sort of an upper bound on the independent set of a graph, of the strong product of the graph. Of course, raised to the power 1 over k. You wanted to get an upper bound of this quantity. The question is there a way in which you can get an upper bound on this quantity? And the point is, unlike the independent set doesn't tensorize. That is, alpha of G tensor k is not alpha G the whole to the power k. It could be much larger than this. And that's why you had 2 for C5, but C5 strong product 2, you had 5. It was not 2 square. But what Lovasz does, suppose we came up with a bound for, the independent set, which actually was sub-multiplicative, or this one, which was not super multiplicative. Like the independent set is super multiplicative. Alpha G tensor k is greater than alpha G to the power k. It was super multiplicative. Suppose I came up with an upper bound which was sub-multiplicative, then can you say something? So what am I trying to say? Suppose what I want to say is, suppose there exists a function f on graphs with the following properties. 1, alpha G is always less than or equal to f of G. So f of G is an upper bound on the independent set, independence number of the graph. And furthermore, so it's an it's an upper bound on independence number. And 2, it is sub-multiplicative, unlike independent set, which is super multiplicative. That is, f of G strong product H was less than or equal to fg times fh. Suppose you had an f with these properties. Then I want to claim, then sigma G is actually less than or equal to fg. And the proof of this is actually very simple to see. What is sigma G? Sigma G we saw was the limit or the supremum of k of alpha G strong product k whole to the power 1 over k. This, by definition of f, this is f G strong product k whole to the power 1 over k. But fg is multiplicative, therefore this is supremum of k fg to the power k whole to the power 1 over k, which is just fg. It's independent of k. So suppose you came up with unlike the independence number, which was super multiplicative, suppose you came up with a bound which was sub multiplicative, and it was still an upper bound on the independence number, then this is actually an upper bound on the Shannon capacity of a graph. Okay. Now let us see, can we lay our hands on such a quantity? Can we lay our hands on a quantity which is sub multiplicative and is still an upper bound on the independence number? Want to claim? We saw one of the bounds which is an upper bound on the independence number already in the beginning of this one. What was it? It was the clique cover number. We saw that the clique cover number, if you recall the clique cover number, chi prime G, which is the chromatic number of the complement graph, or the minimum number of cliques required to partition the vertices of the graph. Chromatic number of G complement. This one, the clique, to work with this guy. This satisfies one, certainly that alpha G was less than or equal to the clique cover number. It was this, because you cannot pick more than one. We saw this already. Alpha G was upper bounded by the clique cover number. But I want to claim chi prime G is actually submultiplicative. That is chi prime G strong product H is actually less than chi prime G times chi prime H. And this is for the obvious reasons. If chi prime G, if you take the best partition according to cliques for G, best partition according to best partition of H into cliques and G into cliques, and take all the product cliques, that will be a partition of G tensor of G strong product H. That will be a clique partition. But they could potentially be even a better clique partition, even a smaller one. Therefore, it's actually submultiplicative. And hence, we will just immediately out of this, we'll get that hence sigma G is upper bounded by the clique partition. So we are getting that the Shannon capacity of a graph is lower bounded by the independent set and it's upper bounded by the clique cover number. Now let's go back to C5. What is the clique cover number of C5? It's a minimum number of cliques required to partition, and in which you can partition the vertices of the graph. So what's the minimum number you can do?
4.
Is it 4? Give me how will you do 4? Minimum.
So I mean, 2 of these cliques cannot have any vertices in common, can they?
It should be partition of the vertices into cliques. Partition of the vertices into cliques.
So I mean, you can have,
must have all the edges. So certainly
you can have 2 edges.
You can do 5. You can break it up, and each vertex is a clique of its own. That's fine. 5 you can
3
do.
is possible.
Huh?
3 is possible.
3 is possible. How do you get 3?
Take 2 edges which are not incident on the same vertex and take the remaining vertex.
So this is possible. So this tells you that chi prime G is less than or equal to 3. I claim 2 cannot be possible, because if 2 is possible, at least one side should have three vertices in it, and you should have if you have 3 vertices, you should have a triangle, and there is no triangle. So in fact, chi prime G has to be larger than 2, and hence chi prime of C5 is in fact equal to 3. So we are now so that puts us in better shape now. So hence the Shannon capacity of C5 is in between square root 5 and 3. So from 5 we brought down the upper bound to square root 3. Okay. What we want to now do is see if we can get, so this clique number was one quantity that upper bounded. It was a sub-multiplicative function on the graphs, which upper bounded the independent set, and hence it upper bounded also the Shannon capacity of a graph. What then Lovasz went on to do was define another quantity. He defined a completely new quantity, which we now call the Lovasz theta function, which was also upper bounded the independent set and was sub-multiplicative. And In the case of C phi, it happened to be exactly equal to square root phi. Okay, so I'll possibly, it's already 11:04. So I'll possibly stop with this. So next time, what we'll do next time is Lovasz introduces something called orthonormal representations of a graph. And then defines the theta function. And it will be easily followed from the theta function. It's an upper bound on alpha g, and that the theta function is submultiplicative. And we'll show that the theta function of C phi is actually less than or equal to square root. So we'll show all of this. And we'll actually go on to show a little more. We'll actually give an SDP formulation. So all of this Lovasz did. He gave an SDP formulation for this. And furthermore, once this formulation was there, it's easy to see that the sandwich theorem, once you give this formulation, you can give the sandwich theorem, which says that, of course, you know, alpha g, this is by definition, the way we defined it, it has this property. We'll show that it is less than the clique cover number. And using this, he went on to prove what was called the weak perfect graph theorem. But that we will, I do not know if I'll have time to do that. This will what we'll do in the next lecture, Monday's lecture. Okay. Any questions?
So this approach is particularly useful if the channel is a typewriter channel or something similar. But if it's something more noisier, then
so it's not for the it's not for the probabilistic model. It's not for the probabilistic. Here you're doing it error free. In that case, yes. Yeah. So this is not for. Then you're asking for a probabilistic channel, no, in which there is probabilities you're going to put on the. You're going to put a probability on the edges. Is that what your question is?
yeah, and also like here the distortion or the noise is sort of look. I mean, so 0 can only go to 0 or 1, but if it's like if it can go farther, I mean, if it let's say it can go to 0, 1, 2, 3, and likewise for all the letters in the alphabet.
But the confusability graph takes into account. No, you draw the edge structures here. The confusability graph asks you, is there a possibility of confusion between these two inputs? If they ever go to the same common output, then it's confused. The confusability graph, I can do it for any such thing.
Yes, no, my question just was that, you know, like in such cases, like going, let's say, going farther and farther, having like larger values of k, it need not increase the size of the independence set.
I think what you are saying is that if the confusability graph is complete to start with, then you will not get any advantage.
Yes. Yeah, if it's complete, then there is no. But yeah. So.
But then zero error kind of decoding is not possible there anyway. So.
Yeah, of course, if the confusability, if the channel was a complete bipartite graph, that means every input could be this one. Certainly, you can't send anything, because then in the zero error model you can't do anything. But if it is the hope is if it's anything less than the complete thing, you can get independent sets which are of size larger than 1, and that will help you transmit things. For example, the moment it's if the confusability graph is not complete, you will get an independent set of size at least 2. And you can now begin doing things in it. The question is now, as you keep growing larger, can you get the Lovasz theta function gives you one upper bound. In the case of C phi, it happens to capture it, but even for it's not known how to do it for other. So it answers a very specific question of Shannon. Shannon asked, this is a very basic problem, and even for C5 we don't know how to do it. The Lovasz theta function answers it for C5. It does not give a general method to answer it for all. It gives an upper bound on the Shannon capacity, but it doesn't tell you how to calculate. The Shannon capacity is NP hard to compute for a given graph. We don't know how to compute it. Doesn't do this. Yeah.
But is it known to be computable? Is it? But it is computable in general.
I think the Shannon graph is computable. Yes, I think the Shannon capacity is computable. It's not efficiently computable. Yes. I believe this. I think I have seen this somewhere. I will check, verify, and let you know at the beginning of.
Because it's increasing, maybe that's how you you can probably estimate how close you're getting.
Yeah, because it's increasing and it's bounded from above.
Yeah.
Yeah, so I think that should give you this
convergence.
Yeah, can it give you? Yeah.
And yes, as I check the growth ending thing, so maybe its proof was not based on STP. It's probably more. Yeah, it may be later on interpreted as that.
Okay. Yeah, for now I've been. So Lovasz doesn't call it semi-definite or any such thing. At least in the first paper, I've seen papers credit semi-definite programming to this particular paper of Lovasz 79. Yeah. Okay. Let's stop with this. We'll meet on Monday.